Welcome to Module 8. Today's module is studying the acids, bases, and salts. Module 8 will be discussed in 3 videos. In the first video, we will cover the following topics: the different definitions of acids and bases, the concept of conjugate acids and bases, the main reactions of acids, and we will also introduce salts. In the second video, we will investigate the electrolytes and non-electrolytes. We will discuss the ionization of the electrolytes and the strong and weak electrolytes. We will also look at the ionization of salts and introduce the pH and the calculations associated with this concept. In the last video, we'll cover titration and neutralization and learn how to write total and net ionic equations. The learning outcomes for Part 1 of Module 8 are: define acids and bases, identify the conjugate acids and bases, and identify reactions of acids. There are a number of definitions for acids and bases. However, we will only discuss 2 of them in detail. The first definition, Arrhenius, is related to aqueous solutions. According to this definition, an acid solution contains an excess of hydrogen ions. Some of the important properties of acid solutions include: they have a sour taste, they turn blue litmus paper red, they are able to react with metals to produce hydrogen gas, bases to produce salt and water, and carbonates to produce CO2. According to the Arrhenius definition, a basic solution contains an excess of hydroxide ions. Some of the important properties of basic solutions include: they have a bitter or caustic taste, they turn red litmus paper into blue, they have a slippery, soapy feeling, and they neutralize acids. Because not all acids and bases are found in aqueous solutions, we need another definition. The Bronsted-Lowry model defines acids as proton donors and bases as proton acceptors. This is a more important definition, and we will keep coming back to it throughout this module. Remember from Module 3 that a hydrogen atom has 1 proton, no neutrons, and 1 electron. Therefore, when it loses its electron, we call it a hydrogen ion or a proton. For example, water can donate a proton and form a hydroxide ion. Ammonia can accept a proton and form the ammonium ion. According to the Bronsted-Lowry theory, the breakdown of acids and bases involves a process where the acid donates the proton and the base accepts the proton. So what happens to the acid after it has donated its proton? It becomes a conjugate base, because this element has the ability to now receive a proton and form an acid again. So we say when an acid donates a proton, it forms the conjugate base of that acid. Likewise, when a base accepts a proton, it forms the conjugate acid of that base. So the formulas of a conjugate acid-base pair differ by 1 hydrogen. Let's look at some examples to explain this further. First, an example of the conjugate base. Water can behave like an acid and donate a proton. The hydroxide ion is more negative than the water, and we call it the conjugate base. An example of the conjugate base: ammonia, NH3, accepts a proton and turns into the ammonium ion, NH4+. This ion is more positive than ammonia, and we call it the conjugate acid. In aqueous solutions, water can act as an acid or a base. For example, HCl is a strong acid, because it has the ability to donate a proton, which binds to a water molecule and forms a hydronium ion, like in the following equation. HCl plus H2O gives H3O plus Cl minus. The HCl is the acid, and the chloride ion is its conjugate base. The chloride is labelled the conjugate base because it has the ability to now accept a proton. Also, the chloride is more negative than the hydrochloric acid. The water is the base, and the hydronium ion is its conjugate acid. If you look at the hydronium ion, you can see it has the ability to now donate a proton. Also, the hydronium ion is more positive than the water, so we call it the conjugate acid. Ammonia is a weak base. It accepts a proton from water and forms ammonium. Water acts as an acid in this example because it donates the proton. The reaction is described in the following equation. H2O plus NH3 gives NH4 plus OH minus. The ammonia is the base and the ammonium ion is the conjugate acid, as it has the ability to donate a proton. The ammonium ion is more positive than the ammonia. The water is the acid, and the hydroxide ion is the conjugate base, as it has the ability to now accept a proton. Also, the hydroxide ion is less positive than the water. Let's practice some examples. What is the conjugate acid of hydrogen phosphate? HPO4 2-. The answer should be A, because according to the definition of conjugate acid, it has to have one additional proton, or it should be less negative. A is the only option that meets this criteria. How about another question? Which are the two Bronsted-Lowry acids in the following equation? H2S plus H2O in equilibrium with HS minus plus H3O plus. The answer should be C. Remember that two acids cannot be in one side of the reaction. So we are looking at one acid in the reactant side and the conjugate acid in the product side. H2S is the acid as it donated proton to the water. Thus, water acted as a base in this case. The hydronium ion is the conjugate acid. So our two acids in this reaction are H2S and H3O plus. The last definition of acids and bases is according to Lewis. It doesn't involve protons or water, but it talks about electrons. Bases are electron pair donors, and acids are electron pair acceptors. For example, the base NH3 donates its lone pair of electrons to the boron trifluoride. We won't go into more detail on the Lewis definition for now. The table below summarizes the three definitions of acids and bases. Now let's cover some of the important reactions for acids. Acids react with certain metals and form hydrogen gas present as bubbles in a solution, according to the following reaction. Acid plus metal forms salt plus hydrogen. For example, 2HCl plus magnesium gives MgCl2 plus H2. Also, acids react with bases in what we call neutralization reactions. Acid plus base gives salt plus water. For example, 2HCl plus CaOH2 gives CaCl2 plus 2H2O. Acids also react with metal oxides to produce salt and water. For example, 2HCl plus Na2O gives 2NaCl plus H2O. And finally, acids react with metal carbonates to produce salt, water, and bubbles coming from carbon dioxide gas. For example, 2HCl plus Na2CO3 gives 2NaCl plus H2O plus CO2. As a rule of thumb, whenever you see CO3 on the reactant side, you can expect to find CO2 gas as one of the products. Write the reaction and balance the equation and predict the gas that will be produced in the following reaction. This is an acid and a metal carbonate reaction, so we expect to get salt, water, and carbon dioxide gas, so the answer should be B. Salts are produced as the result of an acid-base neutralization reaction. The reaction is called neutralization because the solution is neutral, so it is neither acidic nor basic. Example: sodium hydroxide neutralizes hydrochloric acid to produce sodium chloride, which is table salt. Salts are ionic compounds composed of a cation, usually a metal or the ammonium ion, and an anion, not the oxide or hydroxide. Salts are usually crystals with high melting point and boiling points, as we covered previously. Let's practice some examples. What salt forms from the reaction of magnesium hydroxide, MgOH2, and sulfuric acid, H2SO4? The answer should be B. The cation is the magnesium, and the anion is the sulfate ion. Magnesium has a +2 charge, and the sulfate has a -2 charge, so the salt would be magnesium sulfate. What salt forms from the reaction of aluminium oxide and hydrobromic acid? The answer should be B, because aluminium takes a +3 charge and bromide has a -1 charge, so the salt will be aluminium bromide, or AlBr3. This is the end of part 1. Please proceed to part 2, where we will discuss the electrolytes and non-electrolytes.